My name is Sunaina, and today we are going to discuss external data representation and marshalling. These are the topics that we are going to discuss in this presentation: external data representation, marshalling, approaches to marshalling, CORBA's common data representation, and CORBA in marshalling. First topic, external data representation. This topic mainly contains of two questions. The first question is, why does the communication data need external data representation and marshalling? This is mainly because on different computers, different data formats are present. For example, big endian or little endian integer order, also ASCII or Unicode character coding. For example, big endian or little endian, most numbers that you store are larger than a byte, and there is some choice about how you lay out multi-byte numbers in memory. In Big Endian, you store the most significant byte in the smallest memory address, and in Little Endian, you store the least significant byte in the smallest memory address. Now let us see an example. Consider the expression int j equal to 3. It looks like in memory like this. So in Little Endian approach, we write it from uh, right to left, and in Big Endian approach, you write it from left to right. So the most significant bytes are written in the smallest memory address in the Big Endian approach, and the least significant bytes are written in the smallest memory address in the Little Endian approach. The next question is how to enable any two computers to exchange data values. One of the following methods can be used to enable any two computers to exchange binary data values. The values are converted to an agreed external format before transmission and converted to the local form on receipt. If the two computers are known to be the same type, the conversion to external format can be omitted. The values are transmitted in the sender's format together with an indication of the format used, and the recipient converts the values if necessary. The next topic is marshalling. Marshalling is the process of taking a collection of data items and assembling them into a form suitable for transmission in a message. Unmarshalling is the process of disassembling them on arrival to produce an equivalent collection of data items at the destination. Thus, marshalling consists of the translation of structured data items and primitive values into an external data representation. Approaches to marshalling. Three alternative approaches to external data representation and marshalling are CORBA's common data representation, which is concerned with an external representation for the structured and primitive types that can be passed as the arguments and results of remote method invocations in CORBA. It can be used by a variety of programming languages. The next one is Java's object serialization, which is concerned with the flattening and external data representation of any single object or tree of objects that may need to be transmitted in a message or stored on a disk. It is for use only by Java. XML, extensive markup language, which defines a textual format for representing structured data. It was originally intended for documents containing textual, self-describing structured data. For example, documents accessible on the web. But it is now also used to represent the data sent in messages exchanged by clients and servers in web services. So we discuss further about CORBA's common data representation. CORBA CDR is the external data representation defined with CORBA 2.0. CDR can represent all of the data types that can be used as arguments and return values in robot invocations in CORBA. The 15 primitive types that are used in CORBA's common data representation are short, long, unsigned long, float, double, character, boolean, octet, etc. So, the type and how it is represented in CORBA is given in the below table. Primitive types. CDR defines a representation for both big endian and little endian orderings. Values are transmitted in the sender's ordering, which is specified in each message. The recipient translates if it requires a different ordering. For constructed types, the primitive values that comprise each constructed type are added to a sequence of bytes in a particular order as shown in figure. Okay. So the index and sequence of bytes is given. So first, the length of the string is given. Then the datas are given. And again the length of the string, the data, etc. are given, and all those are 4 bytes each. Okay. Now, marshalling in Corba. Marshalling operations can be generated automatically from the specification of the types of data items to be transmitted in a message. The types of data structures and the types of basic data items are described in Corba IDL, which provides a notation for describing the types of the arguments and results of RMI methods. For example, we might use Corba IDL to describe the data structure in the message in figure as follows. So this is the Corba ideal representation of the example given before. Okay. The Corba interface compiler generates appropriate marshalling and unmarshalling operations for the arguments and results of remote methods from the definitions of the types of their parameters and results. These are the references that I used to make the slide. Now let us listen to a video to know more about marshalling.
First, let's look at how we can reduce the overhead in marshalling the arguments and the data copying. Just to jog your memory, marshalling refers to the fact that the semantics of the RPC call being made between the client and the server is something that the operating system doesn't have any clue about. So in other words, the arguments that are actually passed between the client and the server has semantic meaning only between the client and the server. The operating system has no knowledge of it, and therefore marshalling is the term that is used to say, let's accumulate all of the arguments that is there in the call and make one contiguous network packet out of it so that we can give it to the kernel and the kernel can send it out. That's what is being described as marshalling. And the biggest source of overhead in marshalling is the data copying that's going to happen. And I'll explain that in a minute. Potentially, in doing the marshalling, there could be 3 copies involved. Where are these 3 copies coming about? Well, first of all, the client is executing. When a client is executing a procedure, all the arguments for the procedure call that it wants to do is living on the stack of the client. And there is an entity, we've introduced this terminology even before, called the client stub. And the role of the client stub is to take the arguments of the call which are living on the stack and convert it into a contiguous sequence of bytes called an RPC message. So the RPC message has no semantic meaning. It is just a contiguous string of bytes which you can pass to the kernel, and the kernel can then send it out on the wire, just like any other message. So that's the first thing that the stub does, and that's the first source of overhead. The client stub is making the first copy from the stack in order to create an RPC message. Now remember that the client is a user program, so it is living in the user space outside the kernel. And so this RPC message, which has been created by the stub, it is part of the client's address space, which is living outside the kernel. So this RPC message is in user space, and the kernel has to make a copy of the RPC message from the user space into its own buffer, the kernel buffer. And that's the second source of overhead, the second source of copy in doing the marshalling of the arguments. So now it is in the buffer of the operating system kernel. Now the operating system can kick the network controller and say, hey, go ahead, take this buffer, send it out on the wire to the desired destination. And the network controller at that point is going to move the bits from this buffer, which is in the system memory of the operating system, into its internal buffer using DMA. And this is the third copy that is happening. The copy that is done by the network controller using DMA to move the bits of the RPC message copied from the user space into the internal buffer of the kernel. And now this movement is being orchestrated by the hardware to move it from the kernel buffer into the internal buffer of the network controller so that it can then get out on the wire. So those are the three copies involved in